Okay, thank you, Professor, for inviting me to this forum. My name is Rupak Chatterjee. I'm a professor in the Department of Physics and a member of the Center for Quantum Science and Engineering. And I'd like to present you with some research I've been doing on machine learning and quantum physics. I'm one of the cluster leaders of this Center for Quantum Science and Engineering, started by Professor Yuping Wang. I was initially brought into Stevens Financial Engineering Division, and I have moved to the Department of Physics, and my background is in theoretical physics. My general philosophy in my research comes down to sort of three, philosophical areas of how quantum is being used in engineering applications. One is the aspect of quantum information, that is how information data can be held in the state of a quantum system, right? And you can hold many different forms of data, and we have a large number of states of quantum physical systems to hold this data. So that's one aspect of the research. The next aspect is quantum computation. How does one manipulate these quantum states once they're being held in a quantum physical system? And some of the things that we know of that are happening today are, of course, quantum computers, where quantum computers are either quantum gate-based computers, like the IBM Q, or adiabatic quantum computing, which is a different type of manipulation of quantum states. That's the D wave. And the large part of what I do here is the quantum machine aspect that can be executed on these types of quantum computers. And so there's a representation of information, there's a manipulation of information, and a final aspect, which is also part of the center, is quantum communication. How does one transfer, quantum data across channels, either wireless or what have you, once the data has been represented and manipulated? One of the first tests of this quantum communication of our center was performed by Yuping when he shot several photons across the street from Bouchard into the Hanlon lab number 2 across the street in Babbitt. But this is the general philosophical framework of how I look at problems when it comes to the quantum system approach to different ways to analyze data through machine learning. So why would someone want to use quantum systems? Well, quantum systems, through the use of Hilbert spaces, allow a massive amount of data to be represented, especially through a quantum concept of superposition. And so quantum wave functions can hold massive amounts of data, and these quantum wave functions exist in usually infinite dimensional Hilbert space. And so there's a lot of storage possibility to represent this data. There's also extra advantage when it comes to computational complexity. I'm sure some of you have heard the word quantum entanglement, and to create data that's quantum entangled allows one to use non-classical correlations for possibly highly complex structures within this data. And so it's using a quantum system allows you to use an extra type of correlation that is not available to you in a classical system. And number 3, which is usually seen as one of the biggest advantages of quantum computing, is computational speed, right? And so the quantum gate approach and the adiabatic quantum approach allow a certain amount of parallel computation to happen through unitary operators in this Hilbert space. And so there's a large amount of speed up that can be done on the quantum information that is held in a very complex state if it's an entangled or superposed state. And so these 3 aspects are some of the features that a quantum system can bring to classical machine learning. This idea of combining quantum information and machine learning is a very hot topic. This is the cover of Nature, where it says quantum information meets machine learning. And so this is not something that is just a theoretical approach, but is actually being applied. And some of the research that I do with Professor Yu and Professor Yu-Ping Wan, we're actually applying the theoretical algorithms that we have proposed using either Yu-Ping's lab or some of the publicly available quantum computers such as the IBM Q or the D-Wave up in Vancouver. So far, my research in this area has gone along 3 lines. One is quantum systems for machine learning, where with Professor Yu, we have written a couple of papers where we have a quantum approach to support vector machines using quantum optics. Professor Yu is an expert on quantum optics, and so that paper was published a few years ago in Quantum Information Computation. Recently, we've published a paper on quantum k-means clustering using superconducting processors. Those processors were on the IBM Q. With Professor Yu-Ping Wang, we have used some of his photonic systems to perform Monte Carlo simulations. If you've done Monte Carlo simulations, especially for multivariable systems, Monte Carlo simulations require a lot of random numbers, specifically true random numbers. Classical computers cannot provide true random numbers, but quantum systems using the time modes of Professor Wang's photons do provide true quantum numbers. And so we published a paper showing the advantage of quantum numbers. A third aspect of quantum methods for of my machine learning is with a Professor Carter Collado in the School of Business, where we are looking at quantum optimization approaches to study how to optimize, the different types of portfolio optimization when it comes to, large asset portfolios of asset classes of either stocks or bonds. And so that's, the three different approaches where I'm trying to introduce quantum systems into classical approaches using the advantages of quantum physics.